I struggled with how to introduce someone like Ron Jones, and then I realized that in the world of entertainment, there are performers that just go by, the first name. Just say Madonna, and you know who you're talking about, or you say Brittany, or this is
Boswell.
And Ron is one of those guys for our sport. There's nothing I could say that you don't already know. There's nothing I could say that would be good enough to describe his accomplishments in all classes of racing. So just give him a round of applause for all he's done for the sport, Ron Jones.
Thank you. Well, thank you very much. I appreciate that. It's very, very nice to see all of you, a big group, and I thank you all for coming. It's great to be here, and I think that you're going to enjoy this. Uh-oh. Is that okay? It went away. I am only going to speak a few minutes because what I have to speak about is basically the ancient of days of hydroplane and racing type propellers. You'll see a number of propellers here on the table that Ike Keelgas has done a tremendous job of polishing and getting ready for us, and some of them are very, very old. And I'm going to right now hand a picture out that, unfortunately, I put a couple of them on here upside down, but it doesn't make any difference, you won't know. But yeah, I want to pass this picture around, and you just keep passing it as I'm talking. The reason being, unless you have the world's greatest eyes, you won't be able to tell what it says on some of these. These pictures were taken by a friend of mine who was in England at a museum. And in the museum, believe it or not, were propellers, so they took pictures of the propellers and sent me a few of them. And unless your eyes are just absolutely fabulous, you won't be able to see this, so I'll tell you. One of these propellers in the upper left-hand corner is circa 1839, and the rest of them 1855. Frankly, I didn't think there were any propellers until about 1900, but they had propellers way back then, and you can see some of them here. And they had some ideas about what make propellers work, too. There are some of them with holes in them. And I think they must have imagined, and I'm only imagining what they thought, maybe there was a lot of pressure on the blade that needed to be reduced because of cavitation. I don't know. But if for one reason or another, there are holes in the blades of those propellers. Anyway, you'll get a kick out of seeing these pictures that go back that far. In my own case, when I got old enough to know what was going on, what my dad was doing with Slow Motion 4, the one before this one, propellers were a hard thing for him to come by. When I was a kid, he raced limited hydros. And in those days, Stannis, S-T-A-N-N-U-S, Stannis Boat Company, or a propeller company, and I believe they're in Michigan, they were the King Kong propeller makers. And all the raceboat guys bought brass, two-blade Stannis propellers, not unlike what you will see up here that Ike has brought for us. And Dad used to do real fine with those, as did everyone else. Brass, however, has its limitations, and sometimes they would bend. A lot of times they bent, and the owner didn't know it. He wondered why the boat was slowing down, and nobody knew why, but the propellers were bending. The blades were laying back. That was not uncommon. When I got to understanding a little bit about what was going on, the guy that was really the big King Kong that day was a guy named Harold I. Johnson. And his initials were H-I-J, so he called his propellers High J's. And that was the big propeller of the late 40s and 50s and on into the 60s even. And High J was, he provided one of the propellers for Slow Mo 4, and it was brass, a two-blade brass casting on an unlimited hydroplane. You think of it now and you can't believe how it happened. My dad drove the boat the first time it went through the measured mile, And the first run through was 192 miles an hour. Now, nobody wants to believe that, but I know the guy that timed it. And on the return run, the propeller broke, obviously, at that speed, brass casting, and tore the boat up, and the boat hopped, almost threw my dad out of it, and it tore up the back end of the boat, just like today when they go away. Only then the problem was the timers who had come here from APBA, American Powerboat in Michigan, told my dad, now you've got 3 more days and we're getting on the airplane and going home. Well, here's a boat with most of the transom gone, the rudder and strut and all a mess. And somehow, by not ever coming home and staying up 3 days, or 2 days and 3 nights, he managed to get it back together. And next time the boat went in the water, the owner was there and said, you know, you're kind of a nut. You're going 192 miles an hour. I won't have a boat. You're going to kill yourself. Your wife will sue me. She'll take my automobile business away from me. Therefore, I'm going to drive the boat. And Dad says, but you don't know how to drive the boat. Well, you sit over there and I'll sit over here and you can put your foot on the throttle and steer it, but we're not going to go any 200 miles an hour. So they went 160. But the world record was 141, so it wasn't too shabby even then. But to consider they were doing this in 1950 with brass two-blade castings. It's amazing when you think of what the material is today and the amount of effort that it takes to make a propeller today. Right here, you see a forging. And Ken will tell you much more about that later on. And I don't want to take any of Ken's thunder, but you'll see that that's pretty thick. And now, I want to only compare that to you so you'll understand what I used to do when I made propellers. The first boat I ever built was a 136 hydroplane for my good friend John Leach. And we ran it for quite a while, and it was so-so. No great world record holder. It just was a reasonable boat, but didn't go all that fast. One day he and I went to the lake to test, to see what was going on, and I couldn't really tell from the shore what I wanted to know. So when he came in, I said, I'm going to wade out in the water until just my head is sticking out, and then you come by fairly close, and I want to see under the boat. Well, he came by reasonably close. I got real wet, but I did get to see under the boat. And I noticed right away that the strut was about that deep, but the bottom of the boat was only about that far off the water. So it wasn't up all the way as I wanted it to be, a real prop riding boat. And it dawned on me on the way home, thinking about it, what had I seen when I watched this, what was going on. It dawned on me when the propeller gets here, horizontal, it's not doing anything. Two-blade propeller. Both blades are reasonably out of the water. In fact, the thing is probably more of a drag than anything else. So I decided I wanted a 3-blade propeller. So I called around, called Hy Johnson, called Stannis, called anybody I could find. Nobody even dreamed that a hydroplane would ever run such a thing as a 3-bladed propeller. We all know that 3-blade propellers are for tugboats, to carry big loads and to pull lots of weight. But you want to go fast, you want a 2-blade. No, I want a 3-blade. Well, no way out, so I took John's little 2-blade and I took it to a friend of mine who laid it in the sand and made 2 aluminum 2-blades. And this is so crude, and the only reason I'm telling you this story is when you hear what Ken Frankel is going to tell you, you're going to be amazed. I took these 2 2-bladed aluminum propellers and I took a little triangle and drew what I thought was 120 degrees on the end of each hub, and then I bandsawed them to what I thought was about 120 degrees. And I assembled them on a little jig and took them to a friend of mine who had the first aluminum heliarc welder in the Pacific Northwest. This is a long time ago. And he welded those 3 blades together, and of course the first 2 kind of came together a little bit, but we couldn't do anything about that. We thought it would kind of average out. Long story short, we put that aluminum 3-blade in the sand down at Pacific Car and Foundry, and they made me a steel one. And I hand ground as much as I could, and I took the rest of it to Olympic Propeller, and they looked at it and said, "What is that?" And I was, you know, heartbroken. I handed the propeller company a propeller, they didn't know what it was. Come on. And they said, "Well, we'll do the best we can." Well, they did, and it ran really, really good. John Leach went to Southern California, and the Nationals were at Lake Mead. And in those days, the Nationals were a 5-mile course, but it was 2.5 miles around, 1 lap, 2 laps on a 2.5-mile course. And he won the first heat, and all the world record holders and national champions were there. So we learned real quickly what we wanted to know about 3-blades. Well, then when I wanted more propellers, I couldn't get anybody to build them. And gradually another propeller builder kind of fared into the scene. His name was Phil Rolla. He really wasn't a prop builder, but he had gone to Italy and found out that they had some props being made there. So he got involved with propellers in Italy and called them record propellers. And they became a big hit in America. And they worked real well, probably a little better than the High J, and the High J began to fade out. Joe Mascari came along with a propeller called the Carry. And there was even an attempt by a company called Workala. And there is one of those up here. If you get a chance later to look, there's a 3-blade Workala up here, and where the blade joins the hub, they cut a whole bunch of material away. And the plan was to let the force out and let the propeller wind up higher. Anyway, when it became obvious to me that there was no way out, I decided I better learn how to build propellers. I had befriended a man in Tacoma named Joe Trumbley. Joe, maybe some of you remember his name. He's gone now, but he was the woodworking instructor at Bates Vocational School in Tacoma, but he had more head knowledge than anybody I've ever met. He taught my lifelong friend Bob Mackey how to do wood, and there's nobody better on this planet than Bob Mackey. So Joe Trumbley and I went a long way back, and he told me how to build a plug for casting my own propeller. And I know you probably won't be able to see this real well, but you can look at it later. Up here is a shape that you'll see. It kind of looks like a wishbone or something. That's a shape that you can determine by knowing how much pitch you want, how much rake you want. Rake is the, where's the propeller? Rake is the angle. If you put a straight edge along the face, you'll find a straight line, and it'll be inclined, maybe, to the shaft line angle. So maybe it'll be 5, 6, 7, 8, 10, 12, 15, up to 20, maybe even I built some that were 30 degrees of rake. But anyway, from knowing that, and a couple of things that Joe Trumbley taught me, which I have now forgotten. Can you believe that? I'm 75. Why would I forget? We made these wishbones, and then we stacked them up. I drilled a hole in the same place in every one and put them around a round rod and stacked them up into this big pile. And then from an end view, they were staggered. And that gave you the pitch. If you ground in the hollow of each one of these little staggers and got right down to 0, that was the face that you wanted. And then you probably, I hope you can see this. This red line is where we sawed it out ahead of time, so we didn't have to grind all of this over here. And we made our own plugs to put in the sand and make our own castings for our own propellers. I made a lot of those until I graduated, and I made one like that and put 3 blades together, and I wrapped fiberglass around it with high temperature epoxy resin and heat treated it. And then we could inject resin and wax into this mold cavity, and then take the wax out and put it in a ceramic mold, melt the wax out of there, pour the metal in, and we had a 3-blade casting. And I had to do that because nobody else wanted to build them. That is until John Leach's 3-blade propeller showed up on another boat at the Nationals in Seattle, and he won the Nationals with it. And Hy Johnson was there, And he wanted to see, he never paid any attention to the boat, the driver, or anything else. He always walked around and looked at the propeller on the boat. And he looked at that one, and I happened to be standing there, and his eyes got this big. And out came the camera, and he must have taken 100 pictures. He just stood there for half an hour taking pictures of that three-blade propeller, and not long afterwards, three-blade propellers became more available. Anyway, it was difficult in those days. The record propeller, as an example, was made by, he took a bar of steel big enough, my friend Phil Rolla took this bar of steel big enough to each farmer around where this company lived in Italy, and all these farmers had a backyard forge. You know, horseshoes and plowing shares and whatever else they got to heat and bend and bang on. And he gave them a template, and they would take this piece of metal and heat it up and bang and twist it until it fit the template that he gave them. And then they drill a hole in it at his factory, and they put a little template over this rough chunk of bar steel, and they had a drill, and they drilled through, they had a lot of holes in this template, and they drilled through these holes and drill this metal all full of these holes and give it to a workman who hand browned with a disc sander the metal away until the holes disappeared. Then he knew that he was on the money. Now this is how propellers used to be made, and those were record propellers, and it wasn't that far long ago. 60s and 70s they were made that way. And when I was making propellers for three blades, for the Unlimiteds, they were cast. They were a high-grade alloy steel, but they were still cast, and unfortunately they would break. And we did a lot of hand grinding. I hired a fella off the street. He was a friend of mine, a guy named Boyd Winkler, and he had never even seen a propeller. And I tried to teach him how to grind them, and he did a marvelous job grinding propellers. Well, let me tell you, and now this brings me to where I'm going to introduce the guy that knows what propellers are all about. He would grind these propellers, and he would do a pretty good job, and we'd give them to the customer, and they would run the boat and tell us how it performed. And they'd say, we want another one, just like that one. Well, we couldn't do it. I mean, we tried, and we made them out of the same casting, and the same templates, and the same pitch gauge, and I have a pitch gauge like I used to use up here, and afterwards, if you wish, you can look at it. They were very crude, and we did the best we could, and we thought, I had this magic formula. Pitch times RPM divided by 1056 equals miles per hour. And now if the boat doesn't go that fast at that RPM, if it's supposed to go 100 and it went 90, then it's got 10% of slip, we thought. Well, I want you to understand, pitch doesn't mean a thing. What? What did he just say? Pitch doesn't mean a thing. There's a fellow here tonight whom I'm going to introduce to you now. I've been around hydroplane racing, obviously, since I was a kid, and that was 75 years ago. And a lot of people have come and gone, and a lot of folks have made big contributions to the sport of hydroplane racing. Most, if not all of them, have been well recognized. Many of them are in the Museum's Hall of Fame. Some of them are in the Gulf Marine Hall of Fame, or the American Powerboat Association Honor Squadron. A lot of places to be honored for things that you do when you contribute to boat racing. Ken Frankel has, in my estimation, done more for making boats go faster than anyone I know. And let me tell you why I know that. Let's say you got a boat with a certain restricted engine. The American Powerboat Association, as an example, gives you rules that you can use to build your engine. And if you're at the max of those rules, and you're going as fast as you can go, and your boat is 6 inches off the water, flying like it's supposed to, and you just can't go any faster, you could spend another 20 grand on the engine and not go any faster. But if you knew how to make a better propeller, That's where it's at. And Ken Frankel is responsible for doing that. I met Ken quite by accident. Somebody came to my shop one day on a Saturday. The guy was all out of breath and he was so anxious he just hardly could speak, and he had this thing in his hand. He says, "Can you make me one of these?" And the race is tomorrow. I can't. It's a strut bushing. It was all worn out. It was a piece of junk. He said, "I just haven't been paying attention and my strut's all worn out and I'm ruining it, and the race is tomorrow. Can you help me?" Well, it's Saturday and the race is Sunday. I don't have a lathe. I'm not a machinist. I said, I'll look around. I'll walk around Kent, see if I can find somebody open. And I walked around Kent and I found somebody open. And I went in this fellow's shop and I introduced myself and showed him the strut, and I said, "Could you make me one of these?" And I had a piece of material. And I knew right away that he was busy up to here. I could just tell. And I thought, oh boy, what an imposition I am. But he agreed to do it, and so he had one of his fellows take it on and start machining the bushing. Well, while the bushing was being machined, I got to talk to Ken. And I don't make any claim to fame other than one thing. I recognized what he had and who he was. That's my only claim. I said to myself, this is the fella I've been looking for all these years. And so I said to him at the end of the conversation, "Would you be interested in making propellers?" And he said, "Well, I don't know anything about propellers, and I'm a sailboat guy." I said, "I know, but I believe you can do it. Please think about it." And when he finished the bushing, I took it to the guy, and he was happy. And I didn't hear from Ken for a while. I don't remember exactly how long it was, 8 or 9 months, maybe a year. And one day he walked in my shop, and he had this little thing in his hand, and it was the most beautiful little aluminum 3-blade propeller model that you have ever seen. I almost broke down in tears. I couldn't believe it. It was awesome. And he had spent all this time learning propellers. And then he made this beautiful little 3-blade propeller. I knew right away the world was in for a treat, and sure enough, in 1989, and I'll let him tell you the rest of this, and the guy that drove it is here, so he can tell me yes or no. But in 1989, there was a real fast boat around here, an unlimited. A guy named Chip Hanauer was the driver. It was called Circus Circus. And it was a fast boat, and it won the national championship. Make a long story short, with their best propeller, Chip tested it. Then they put Ken's propeller on. And it was in the neighborhood of 11 miles an hour. Same pitch, same diameter, same everything, but it was way faster. And I would like you to give a hand to the guy that I believe should be in one of those halls of fame. And if there are any shakers and movers around here tonight that have anything to do with this museum, here's what I'd like to suggest. I'd like to see a propeller cavity, corner, area, something designating propellers and show the history of propellers. And it ought to be called the Ken Frankel display. And if anybody deserves a round of applause, our next speaker, you're going to enjoy this more than you can believe. Ken Frankel, come on up. Have at it.
Thank you. Thanks, Ron. Let me gather a few notes here, and we've got a few things to hand out. I'm pleased to say that Dixon has been able to join us, so I'm going to try and go through my talk here, and Dixon has an interesting session at the end of this that will hopefully be made even more interesting by what I'm going to go through here. I'm going to pass out just one little sheet here. Maybe everyone can send these around. I'm not sure we have enough. And I need to move, JR, you, this and this? Yep. Thank you. Okay. Pull out one more thing here. Okay. At some point we'll probably pass around one or two of these propellers. I'm going to caution you that I don't know how many propellers I've made, probably 60 or 70. I think I've cut myself a bare minimum of 2 or 3 times on every single one I've ever made, so please be careful. Okay. Ron was kind enough to get me involved in this 19 years ago now, and he gave some information about what led up to that. I'm going to go through how we got involved, what we did, and then we'll discuss some basics of propeller geometry and operation. Spend a few minutes just taking a brief look at how we model and manufacture these today, and discuss some of the problems with propellers and manufacturing them. We started in this originally to make a propeller for Circus back in 1989. I believe we were engaged approximately March 15th of '89 to do this. And we wound up producing a propeller, I think about the 9th of May of '89, so a little less than, on the order of something less than 60 days subsequent to that. Ultimately, there were 14 straight days I didn't leave the shop before midnight to get this done, and we had no idea if it was going to work or not. But it turned out to be a very, very interesting project. As we got into it, I tried to quickly survey what had been done and what information was available on the topic. As Ron indicated, the methodologies up till then were fairly crude. The state of the art at that time was to machine these from a pattern using what was called a tracer mill. And for those of you who aren't familiar with how these things are made, in general, they are made by conveying a cutting tool across the entire surface of the blade using a technique usually called hem stitching. And fundamentally, what's going to happen... Anybody a pen? Thank you.
There you go.
So, if this were to represent the cutting tool, it's a little small, but this tool would be spinning, and it would be rotating. This would be fixtured in a machine at some presentation, and the tool would simply make a multitude of passes to painstakingly remove this material. In the roughing stages, we could remove it fairly quickly. As we got down to the finishing stages, the process would slow down considerably. And to give you an idea of the size of the project we're talking about, this is a pretty refined forging here, which I won't attempt to pick up because I probably can't. This weighs, I think, on the order of 120 pounds or thereabouts. The forging that we started with originally, I believe, was in excess of 200 pounds. It was a bidirectional forging. That's going to go from that all the way to something that looks like this. So the vast majority of the material is going to be removed. It's a very laborious process. We were going to try and improve on what had been done. So I did a little bit of research, try and find out what we could find out. Here's what we knew to start with. I knew nothing about propellers. I was certain of that, and to be quite honest, 19 years later, I really don't know a whole lot more about propellers than I did then. There was very little written material available on the topic. My recollection is at that point in time there were 3 test tanks in the world that were capable of testing these in a scientific manner. And we're talking specifically about something which is called a surface ventilated propeller. We'll dive into that a little deeper later. But the information that I was looking for was not information that was going to come from research on a tugboat propeller or cruise ship propeller. These were high performance propellers. there weren't propeller designers out there that I was aware of that were willing to share any information. In fact, I wasn't aware of any propeller designers, period. So, or at least people who claim to be a propeller designer. The bulk of my information came from Ron Sr., who had a very good history of what had been done, at least could give us quite a number of data points. What we did find out was some interesting information. First, that there was no design that seemed to be particularly better than any of the others. Part of that probably came from the fact that most people who had propellers really didn't even know what it was they had. They would have a propeller, but there weren't good techniques for measuring it. So it was not clear what it was you had, even when you had a good one. People generally would try and make several identical propellers, but usually they weren't able to do that, so the anecdotal information was that they would, make 3 or 4, find one that worked the best, save it for the important race. Generally they couldn't measure, there were no observable differences between the propellers. Okay. And then also noteworthy was that the best propellers from different places all seemed to perform at about the same level. Their performance was roughly asymptotic to the same to the same standard. And then finally, the people that I was able to talk to that seemed to be experts, at least by reputation in the field, it was clear that their knowledge was somewhat limited, as they would frequently offer information that was simply factually incorrect, not information that was specific about a propeller, but just basic geometry that was involved in a propeller. And so I could tell that they simply didn't know. Okay, so what did we conclude from this? What I decided was that the design of the propeller couldn't be as important as it seemed to be. The problem was a very, very different problem than I anticipated it was in the beginning, which is that we had to come up with a good design for the propeller. It became clear to me that the design couldn't be that important because nobody had designed one that seemed to work particularly well anyway. It was really more a set of data that was virtually irreproducible. So what we settled on was the execution. And we decided that we would try and make a propeller the aerospace way, whatever that meant. We'd start with good material, we'd use as good a technique as we could, we would try fundamentally to simply make all 3 blades the same, and we would be certain that we knew what it was we had made. So if we were somehow fortunate enough by randomness to get one that worked, at least we could repeat it. Additionally, we would copy the basic design parameters that people had some success with. So these were basic characteristics of pitch, rake, diameter, general plan form, etc. So we expected to wind up with a propeller that basically looked like what everybody else had, but had differences that were there but difficult to measure that would make it somewhat better. The advantage of this, of course, was that I was pretty confident that, well, once you make one and sell one, of course, it's out there in the world. The only remedy for that is to make it and rent it out and then put it in a little box and carry it around with you all the time so nobody else can see what it was. We weren't planning to do that, so we knew that whatever we made would be available to everybody to measure as they cared to. But my suspicion was that if they hadn't been able to discern what made them work up till now, they probably wouldn't be able, they would probably be hard pressed to see what it was in there in our new design, or in our new series of these things. Okay, so basically we were going to set off on an evolutionary path to do this. We were hopeful that the first results wouldn't kill us financially, and we'd continue to be a player in the game, and then we could evolve this. And I was hopeful that after several tries we could get something that at least would be competitive. All right, so what happened? The boat we made this propeller, as I said. I think we started the 15th of March, finished it the 9th of May. I believe the race it was on was Houston, and the propeller, to be quite honest, looked quite fragile. We made it to the numbers, but to look at it, it looked like it probably was going to blow up. So this was done for Circus Circus. Again, this was a design of mine. A gentleman named Eric Anderson at our shop was a young fellow that was very involved in the project, did an excellent job of machining it, and we sent this off to Circus Circus to try. And fortunately, I think they were a little bit reluctant to try it, but fortunately it got on the boat, it worked reasonably well, and it didn't come apart. So we lived to play another day on that. And my recollection is that the next race was, I don't recall if the next race was Miami or if the next race was Detroit. Can you help me there, Chip? What, probably Miami. In any event, by the time Detroit came around, we made another version, and that propeller sort of became a standard for years to come. All right, so that was our brief history in getting into this. So now let's talk about the basics of propellers. Yeah, boy. Sorry. So, first thing is why is it even important to begin with? And Ron, I think, touched on this a fair amount. Our belief is that the propeller is probably the least expensive way to go faster. So the impetus to pursue propellers really is an economic one. Of the several things you can do to the boat, at least at that point in time, it appeared to be the best opportunity financially. Our goal was a pretty simple one. We were going to try and maximize the thrust that could be generated out of the propeller for a given amount of torque that was input. It sounds very simple, but that's how we were going to drive our, that's what was going to direct our path on this. Unfortunately, since none of the boats were instrumented for measuring torque and thrust, we really had to measure these by secondary effects. So we're looking at lap times or straightaway speeds, time through the corner, whatever measurement we could come up with. Okay, so that is why we were pursuing this. All right, so now let's take a look at sort of some basics of what goes into a propeller. And I'm going to go through just some terms pretty quickly here. I think propellers probably have more anecdotal and mythical information about them than just about anything else that goes on a boat. Maybe if we just walk through some terms quickly, at least we can set a few of those to rest. Just using this as a demonstrator, first obviously is the diameter. The diameter is going to be the maximum span of the propeller. Every propeller we've made, I won't say that it necessarily has to be this way. Maybe there's an opportunity to do something a little different. Generally, propellers tend to be symmetrical. So one would expect the radius from center line to this tip to be the same as from here, from center line to this tip. Although I don't know that it necessarily needs to be so. It's interesting to try something a little different. Typically, well, we'll leave that for the moment. Next item is the common one everybody talks about, which is the pitch. And the pitch could occupy a 2 or 3 hour lecture all by itself. But fundamentally, the result of the pitch is going to be that as one rotates the propeller, it will tend to advance through the water. It's obviously designed to be rotated in one direction only. And as one does that, the intent is that you will drive the propeller through the water. The pitch could be spoken of in all sorts of terms, but as a resultant effect, it would be simply how far the propeller advanced per rotation. Okay, so a propeller which was a 20-inch pitch propeller would be expected, in loose terms, to advance 20 inches, meaning 20 inches this way for every rotation of the propeller. A 25-inch pitch propeller would be expected to advance 25 inches. The pitch is, if we look at the blade itself, we can speak of the pitch being simply an item of geometry. And in this, if we were to place a rigid body proximate to the propeller, in fact in direct contact with the face, and this will be called the front face or the pressure face of the propeller. If we were to rotate this propeller a given amount, we would note that it would drive itself forward a given amount. That relationship, more specifically, would be the pitch. This is absent any hydrodynamic effects. We could place a ball bearing next to this, we could place a pencil, we could do all kinds of things. That means then that we can really look at this in somewhat more mathematical terms. And what we're going to do then is we're going to say for a particular amount of rotation, if we were to look at a particular radius on the propeller, pretending, for example, that we're an element of water at that point, as this propeller rotates a given amount, how much do we drive up the face of the propeller? Meaning, how much do we move along the axis of the shaft of the propeller? The pitch can get quite complicated, except in the very simple case where the pitch is uniform in the propeller. Typically, propellers are not that way. They typically have what will be termed progressive pitch, and they typically start at a lower pitch and then rise, and sometimes very sharply, towards the trailing edge. Progressive pitch refers to this tendency, well, not tendency, to this design of lower pitch in the beginning of the rotation at what would be called the leading edge here, and then finishing at a higher pitch at what would be called the trailing edge. Given that the propeller is going to rotate in this direction, this will be termed the leading edge all the way out to here, and this will be termed the trailing edge back here. Okay, there's another item called rake. One thing I would note is that this propeller, although it looks very, very curved, is actually composed of straight lines on the pressure face. It doesn't have to be, but all of ours are. And this can be shown by just taking a straight edge, and one will find, try to do this without scratching this thing up, that although if you do this like this, it certainly doesn't fit. When you rotate this around, you will find a point where the straight edge happens to fit perfectly. And this can be somewhat of a surprise. All right. One can design the propeller such that these straight lines intersect the hub. They could be ahead, behind, of hub center line. That would cause another item called skew, but that really isn't of great import here. Now, if we look at that straight line, in the simple case of a propeller whose pressure face is a ruled surface, that is the name for a surface composed of straight lines. If we look at that straight line, and then we look at the angle that that line makes, see if I can do this here so anybody has a chance of seeing it, to the shaft, this angle of inclination here is termed rake. So without trying to get too deep into that, let's just look at two propellers of different rake. These propellers, interesting. Two propellers here, presumably the same pitch, is that correct? Nominally so? Yeah. Okay. And yet these propellers are of different rake. You can see how one blade seems to trail the hub dramatically more than the other does. All right? It doesn't change, in and of itself, it doesn't change the pitch of the propeller. It has some other impact. In fact, what it tends to do is it alters. If one were to construct a vector, to construct something that represents the total force generated by the blade, or the force generated by the blade hydrodynamically at any point on that blade, you would find that the vector representing that force changes based on the rake. Just as it would in an airplane that had dihedral or no dihedral. If the wings are up like this versus like this, the lift vector is going to be going like this instead of like that. That has some impact on how the boat operates. Okay, cruising down here then, the rest of these get pretty simple. The blade profile is simply what this appears to be. This could be shaped all kinds of different ways. So the blade profile is what happens when we look along the shaft center line and view the blade. The thickness or thickness profile, thickness would refer to the distance from the front face to the back face, from the pressure face to the suction side. And in any racing propeller, you would find that thickness varies all around the propeller. It tends to be very thin at the leading edge, tends to be thicker at the trailing edge. That thickness profile, which could be a massive amount of data, may bear very heavily on how the propeller performs. Hub diameter, one can envision a large hub, a small hub. Typically one tries to make a small hub as possible so it doesn't drag in the water. We've already discussed leading edge and trailing edge. There is something called cup, which is often can be beneficial and is present historically is present in fact, been present in every racing propeller I've ever seen, other than the ones that we did explicitly. But the cup is essentially a dramatically lifted surface at the trailing edge, and it's done for a variety of reasons. There's good things about it and bad things about it. This propeller, you don't see any dramatic lifting of that edge, but in fact, the pitch, this propeller does in fact curve up somewhat at that trailing edge. All right. Final thing here is how many blades. And this is probably gets into an area of the most arguments in propellers. I'm not even going to get too involved in it. Normally we would make a propeller with as few blades as possible. The fewer blades one has, the more load is on each blade, so there may be structural implications. The more blades one has, the more likely that any one blade, well, we know the blades are not perfectly similar, so while one blade may be trying to push you ahead, the other four may be trying to slow you down. So there's some risk in, you generally don't want to put any more blades in than you have to, but that's again, that's a whole other topic. All right, now having done that, let's move to what the propeller is doing on the boat. And Ron, I don't know where Ron is. Oh, here he is. Very good. Okay, so we're going to look at something. We're not trying to explain a bunch of things here. We're really just trying to show how many questions there really are in this. If we were to look at a boat with a propeller on it, and yeah, thank you. And let's presume that this propeller is simply, the boat is running horizontally and on the surface of the water. And we have a propeller operating here. So one could envision the shaft as it shows here, the boat moving horizontally. And you can see here the propeller happily spinning. And we're going to presume again that we're talking about surface ventilated propellers. So we have perhaps the level of the water somewhere about where my hand might be. I don't know if all of you can see this. But we're going to have the propeller half submerged or less. Okay, and we mean on average, because obviously it's changing, you know, every moment in time. Okay, now if we look at that, and Ron can demonstrate here, I think, you'll see that the blade presents to the water the same on both sides of this. He's got a little device here which will demonstrate how that blade is oriented, and we'll look there, and then we'll look on the other side.
Same angle.
Same angle, okay. Now, if we take that same propeller and put it on a boat as it normally runs on a boat, the boat necessarily, I shouldn't say necessarily, often will have some shaft angle. The propeller is going to be lower, generally, than the engine. And so in order to connect the two, we have to angle the shaft down. Now, as you may recall, a little while ago, Ron indicated that pitch is a often overemployed term here. If we look at this now, and again, we have shaft center line. Remember, the boat is going horizontally. And everyone can see this, I trust. So this is with a shaft center line. I think here we may be illustrating at 9 or 10 degrees. Okay, so now if we compare the original angle. And possibly you can see it's not even remotely close. Okay? All right, now that's on one side of the propeller. All right? So on this side, the propeller.
Let's measure that, what it's supposed to
okay.
be. This is the angle as built when it was on that other straight shaft. And that's what you would do when you built the propeller. It would be all done relative to a straight shaft. But you put it on the boat with an inclined shaft angle, and suddenly the dimensions get different. The pitch gets different. That's why we were saying pitch is not that mandatory of a term to use. This is the one that we originally built the propeller by, but this is the pitch that it takes now because of the shaft angle. And those two are drastically different. There's one, there's the other. But worse,
now it gets worse.
Worse than that, On the way out, that was on the way in, the water, and the water line, as Ken said, was approximately right in here. On the way out of the water, things were drastically different. In order for, see if I can even remember how to do this one, it's so far off. In order for that to fit, that angle is what it takes. Well, here's the angle that was made on the machine. Laid back like that. Here's the angle that is coming out of the water. Drastically different. What does that say? As it entered the water, it was some pitch, not the pitch that was stamped on the propeller. As it's coming out of the water, it's an entirely different pitch, way less. You take it from there.
Okay. So this is a further complication. And this impacts the design. I won't pretend that I know how to design around this. But you can see that the design represents quite a compromise. The less the shaft angle, the less this is a problem. Okay. We spoke of submergence briefly. A few more terms here, just breezing through these. Angular velocity, that's the speed of rotation, RPM, radians per second, revolutions per year, whatever you want. Forward velocity is the speed and the direction that the vehicle itself is going. Not the propeller, but the vehicle itself. And as you can see here, if we convey, if this is our boat, and we convey this with the boat horizontal, the propeller is producing thrust along the axis of the shaft, and yet the boat is going at a slightly different direction than that thrust line. Okay? That's not necessarily bad, but that's of interest. Right? Okay. We're going to talk for a moment about what we're asking the propeller to do, or what gets generated by the propeller. As this rotates, several things are happening. One, again, remember this is a partially submerged propeller, and it's going to be on a shaft angle. All right, so it's generating thrust. The thrust is going to occur along the shaft angle. We can measure the horizontal component of that. There's also a vertical component of that, meaning that the propeller is trying to lift the back end of the boat. It's trying to screw itself out of the water. It's also trying to it's also generating a lateral force. As this propeller rotates like this, and again with partial submergence, so we'll put it here perhaps, one can see that it's trying to, or it may be trying to walk itself sideways. All right? It's going to generate a force laterally. That's going to be a function of submergence. It's going to be a function of a number of other things. And that force will have to be counteracted by something else, either by aerodynamic forces on the boat or by appendages on the boat, which unfortunately tend to generate a lot of drag. Okay. All right. These final terms here are ridiculously abused. My guess is that they're used with proper knowledge less than 10% of the time. I'm not going to claim to be an expert on them. The term slip has come up a few times, and in a little while Dixon's going to engage in this a little more directly. But fundamentally, slip means how far does the propeller advance per revolution compared to how far we believe it should advance theoretically. And you can see that the theoretical issue has gotten very, very confused by shaft angle, by the fact that the propeller may have different pitch at varying places in the propeller itself. So when one talks of the pitch of the propeller, for any modern racing propeller, you really need to specify precisely where on that propeller, where on that front face, you're talking about the pitch. Because the pitch is not uniform on this at all. So you need to make sure you're using the same scheme to observe the pitch if you're trying to do any developmental work with this. If you're really going to make life miserable for yourself and whoever you're trying to get to help you. Cavitation is a circumstance where, as the word implies, there is a cavity. Where in a liquid, a place where the liquid is not present, in combination with a a hydrodynamic device like this would be something that we might term as a site of cavitation. Typically, this means that the water is not flowing or is not proximate to the surface. This can be important for a whole variety of reasons. One of the problems with it is that cavitation usually occurs is a circumstance where we have very low pressure. With nothing there, the pressure has dropped, or nearly nothing there, the pressure has dropped. When you drop the pressure with water present, it lowers its boiling point. And you can drop the pressure low enough that water will boil at very low temperatures. That in itself isn't a problem, but boiling is a violent phenomena, and at a very sort of a micro level, there's a lot of energy involved, and it can damage it's a powerful enough event to damage materials such as high-strength steel. Supercavitating refers to something where you intend it to be that way, and you may generate a much larger bubble, as it were, or cavity for this, whatever hydrodynamic device it is, for it to operate in. That may be done for some very good purposes. Surface ventilated is really what we have for partially submerged propellers. And here the intent is we're going to bring this propeller out of the water for several reasons. One is to minimize drag on every blade that's not in the water. And the other is to entrain air as it moves around. If we have this propeller operating, and we described what we called a pressure face, the driving face of the propeller, the front face, we want water to be proximate to that. But we really don't want water to be proximate to the other side. In fact, we'd prefer nothing was there. We don't want to have any skin friction drag on it. We don't want to have anything opposing the forward motion of it. A nice way to do that is to bring this propeller out of the water into the air, and you'll tend to entrain air with it and draw some air into the water on this front face. The high pressure of the water if I just said front face, I meant the suction side here, I'm sorry. The high pressure of the water on the front face or on the pressure face will displace the air, and so you don't diminish the performance doing that. Okay, so that's a litany of terms there. I'm going to hit on just a couple terms real quickly in manufacturing. These get a lot of abuse as well. The first two, cast and forged. Casting is a process where you melt it. All right. Forging is a process where you basically beat the crap out of it until it moves around to where you want it to go. All right. Pretty simple. Casting works above the melting point. Forging works below the melting point. In terms of the mechanical properties one develops in the material, meaning what its strength capabilities are, what its fatigue characteristics are, forging is preferable to casting. You get greater density, you get greater refinement of something called the grain of the material. There's a variety of other good things that go with it. I won't pretend to have a PhD in metallurgy and go into that. Forging is preferable. That's why a forged propeller is often referred to as a better propeller than a cast propeller, because the mechanical properties are better. There are a number of things you can do both to castings and forgings to improve their mechanical properties. CNC machined refers to a process whereby you convey a cutting tool over the surface of the part under computer control. And this is the way most machine tools, most modern machine tools work. It's a very accurate way of machining something. It's a very predictable way. Tends to be much faster, and tends to be much safer. You don't have chips and coolant flying over you because you can put this in a house basically and stand clear of it while it happens. So that is the modern way of doing it. Lab finished is some holdover term about which I don't know much, but to the best of my understanding, it refers to an attempt, even I guess to this day, to take a surface which is not terribly precise and to improve it by some hand finishing. Okay? Anybody who's done a serious amount of CNC machining would virtually never think that they can improve on what the machine did by screwing around with it by hand. Lab finished, I think, is supposed to impart some greater aura to this, as if one is carefully measuring this while you're doing it, as if you're doing it in a laboratory and presumably measuring the part, and keeping track of it. it may work. My preference would certainly be to simply machine the part properly to start with, and then to put yourself in a circumstance where so little material has to be removed to properly finish the propeller, meaning to impart the desired surface finish to it, that you're not going to alter the geometry in any significant ways. And in this case, we're talking about moving something, disturbing it no more than a few thousandths of an inch probably. All right. Now, I'm not sure how we're doing on time here.
The pressure face is
yes.
back of the propeller. It's the one that's pushing the...
That's correct. That is correct, yeah. The pressure face is that face from which we are trying to get a reaction from the water, absolutely. Okay. Let's see here. This will come to life. Take a moment here. The first process in developing the CNC cutter paths for a propeller is to have something to develop those cutter paths from. So what one does is produce a computer model of the propeller. This would be akin to producing a clay model or something of that sort. We're just going to do something that we can use and produce some cutter paths from. Okay, well, let's see here. This would be deemed, I think, the most precise way to do this these days. And for the complex geometries that we're producing now, it's really about the only way I know of to do this. Do I need to press a button here? Okay. The computer model can be used, obviously, to sort of look at and try and visually assess what we've got for the propeller, but mostly we're going to use it to generate cutter paths for the machine. Okay, I'm sorry. Can people see this okay at this point?
Yeah.
Okay. All right, so what we've got here is a very simple one blade. You'll see one blade right here near the diamond. Oh, wonderful. And then we have another blade rotated to this position here. We only have that for manufacturing purposes, okay? This, I'm not trying to make everybody nauseous here, but we can look at this fairly closely. If we zoom in, you can see that even that leading edge has some thickness to it. It's a little hard to see there. This has a number of other things on it. Let's bring this down here. There we go. Okay, we can see the trailing edge up here. See the leading edge here. We have the hub. Obviously, we have a fillet in the hub. If we go away from a solid model here, there are a number of construction lines in here. It's a little hard to sort of see what's what, but as I move this around, you can see that there's some thickness here. And if, for example, we look at, say, that line and that line, you can see that those are corresponding lines on the pressure and on the suction side. I didn't mean to do that. Didn't mean to do that. There we go. Anyway, this then helps us produce our CNC cutter paths. So now, having done this, we get into what looks to be the same, but this is a different portion and a different section of software where we're actually going to produce the cutter paths that will drive the machine tool. And this is where it can get pretty complex. This looks pretty similar to what we had. We've got a few little extra surfaces, which are protection surfaces or driving surfaces here on this. But then if I turn on all the construction planes, you'll see what had to get generated to produce all of this stuff. I don't know how many of them there are there. I'd probably start crying if I really knew. But this is all necessary to produce a cutter path. And then in this, what one can do is, and I haven't even looked carefully at this, but we can produce a path that will allow us to sort of see what's going on here. And so let me move a few things out of the way and rotate this around. We've got this is designed, here we go. So this is going to be cutting the back side of the part. And this is intended to represent a cutting tool here. I'll make this a little smaller, and we're going to start this moving so you can sort of see what happens. This allows us to simulate in the computer what the machine tool is going to do, and this is literally what it's going to do. You can see lines of code screaming by here, and you know, so there we've got 1,200 lines of code just to do a very small section of this propeller, and that might be either a finish or a roughing pass. That is the purpose. That's really what we're trying to get to with all of this. So I'll leave that at that here, and see if we can finish up on a couple other matters. Okay, and are we in a 10-minute delay for lights again? In terms of brand, all sorts are used. Any modern machine tool will do that. You know, we happen to have Okuma's, but virtually any modern CNC mill will work. Okay, so let's get to sort of the last part of this. So what makes this what makes this whole propeller thing so difficult, besides simply manufacturing the propeller? One is you've got a very large dynamic range that the propeller is operating under. The maximum and minimum speeds of a boat, whether it be an unlimited light, an unlimited, a much smaller boat, broad range. The slow speed on the course versus the high speed on the course could easily be a multiple of 2 or more. All sorts of things are changing on the boat. The attitude of the boat is changing, the pitch of the boat is changing, the submergence of the propeller is changing as the ride height changes. And we have one propeller that has to operate around the entire course and work well. So that's one thing that contributes to difficulty in designing these things. Some others, it's very hard to understand what's really going on. We can't visualize the flow very well. I certainly can't produce a mathematical model of the flow around this propeller. Even very simple things, as we have seen earlier, alter the flow. The fact that the propeller is partially submerged, the fact that there's a shaft angle, all make this somewhat difficult to understand what's really happening. It's also very difficult to measure the fundamental forces that are being generated by the propeller. We talked about thrust and lift and lateral force. To the best of my knowledge, there hasn't been a raceboat that has been instrumented to measure these things, although it really wouldn't be all that difficult to do. If one were to do that, you could instrument the propeller shaft so you could measure the torque being input. You could measure the thrust being generated. You could even, if you really want to, measure bending moments at the strut to determine what the lateral forces being generated were. But you'd really have a dynamometer for a propeller, much as you have engine dynamometers, which of course no one would think of developing a racing engine without a dynamometer. But people have been beating their heads against walls for years trying to make propellers with no proper dynamometer. On top of that, people aren't terribly interested in testing. It's difficult and expensive, and most people build race boats to go racing, not to go testing. I don't care much about racing. I'm really more interested in the testing part of it. Also very difficult to test the propeller in isolation. The best circumstance we've come up with so far to really test the propeller comprehensively is to put it on a boat and test it. And we've already noted many things about the propeller that we'd like to measure or learn about, but the truth of the matter, what are we really doing when we observe its performance? We're clicking a stopwatch, and that's generally about all we're doing. We may be observing speed, we might be observing a few other things, but usually that's about it. The propeller has all sorts of loads on it that as a structure make it difficult to design. It's subject to inertial loads, meaning as one spins this, it's trying to literally separate itself, fly apart as any flywheel would. There are hydrodynamic loads imposed upon it from the water. There's hydrodynamic loads that are impact loads, meaning this is not a steady state condition. The loads vary dramatically. I could only hazard a guess as to what the range of those loads is. Dixon may have a better idea, but it wouldn't surprise me if those loads from steady state to greatest impact load might be a multiple of 3 or better, which means you're imposing very high occasional loads on the propeller, and of course it's going to fail typically will fail from that. It's also in a fatigue environment. Fatigue means you've got an alternating load and you're subjecting something to repeated cycles of that alternating load. Again, this is surface ventilated, it's going in and out of the water. The loading is changing even as it goes through the water, but certainly it's changing from water to air and back again. As one cycles that, it can be very hard on certain materials. Most people can't, tear a paper clip apart in one shot, but they can easily bend it 10 or 20 or 30 or 40 times until it fails. And that mechanism is not unlike this. In fact, we'll send this thing around if you just make sure you don't drop it on yourself. And you will see on one edge here there's a fatigue crack already. This is a drag boat propeller. In fact, set the world record in 1995 or 6. 213.9 miles an hour on I think a 19-foot boat. 2,700 horsepower, 19,000 RPM at the finish line. That propeller lasted for what to us is a very long time, probably about 300 seconds. Okay? But 300 seconds for a boat that does a pass, in 5.5 or 6 seconds, quite a number of passes. So that was really a very inexpensive way for that team to go fast. They have a $40,000 engine, that's about a $6,000 propeller, and it made a lot of passes on it. So, anyway, okay. Final item I'm going to hit here very briefly is what's ahead for propellers. And the truth of the matter is, at least from my end, although I've certainly learned a lot doing this, I have not made a lot of progress. What we make today isn't going to be a whole lot better than what we made 19 years ago, knowing next to nothing. There's a lot of good work to be done, I think. It's just an enormously interesting problem, one of the most interesting problems I've ever encountered in my life. A number of things, I think, are areas of progress. One, I think, will be improved materials. There are improved materials available. Lower shaft angle, certainly something that would help. Larger diameters, higher pitch, slower shaft speeds. I mentioned instrumenting a propeller shaft so we can really learn what's going on and quantifying some of this would be a big help. There may be an opportunity to provide some torsional springing or damping to reduce impact loads. Multi-speed gearboxes would dramatically simplify the design of the propeller because you could operate the propeller at different speeds around the course without changing your engine speed dramatically. And there's a whole slew of new manufacturing methods on the horizon that I think can be applied to this. So anyway, I'm going to turn this over to Dixon. I don't know if we want to take a break at this point. I'll let everybody else work that out. There's obviously tons of technical detail in this, and if people are interested and want to know something more, I'll be happy to deal with that afterwards. I don't want to bore everybody else with that portion of it. So appreciate your attention on this, and Dixon Smith from Hydroplanes Incorporated, who has a very, very long history of dealing with this, has some very interesting things.
Dixon for sound, so why don't you take 5 minutes? Okay?
Yeah, everybody take a quick break. Yes, sir.
Very good. Thank you.
Yeah, turn it on. What do I need to do? Less forum then. For those of you folks who don't know me, I'm Dixon Smith. I currently work at the Boeing company as a navigator, which is kind of a weird deal since modern airplanes think they don't need them. I worked on the Budweiser Raceboat team for a long, long time until we lost the sponsorship, doing a whole lot of work. I also happen to own the 1962 Bardol that's been restored and running currently. So my boat racing experience goes from the early 1960s to present, so that kind of gives you a little bit of an idea of how old I am. Ken and I have worked off and on together, traded ideas. We both have done propeller design somewhat independently with slightly different philosophies, but came up with pretty much the same idea of how things should be done. And we've had reasonably similar results. So I tend to agree with Ken that there's probably not a magic propeller design. We've seen several slightly different design philosophies that have produced pretty reasonable results. What seems to be as important as anything, once you get some of the basic fundamentals sorted out, is making the propeller, all three blades, the same, and controlling the shape very, very carefully. And that cannot be done by hand. That has to be done on a CNC machine. And something that Ken just brushed against is the difference between cast and forged. There's a huge cost difference. And one of the things is a cast propeller, you can make a mold, you cast a propeller, you give it to somebody who has a hand grinder, and they spend some short amount of time grinding on the blade to make it look nice, polish it up, and off you go. A CNC prop, forged CNC prop, as you can tell from what Ken said on the design side, the cutter path side, and then the cost of the machine to actually machine the propeller, all of those add up very quickly. So you end up with a considerably more expensive propeller because of the manufacturing process. But what you get out of it is a propeller that all three blades are the same, and you can also manufacture several propellers that will actually behave the same. So any of the boat racers who bought cast propellers from, for instance, Mercury or somebody else, knows that if you buy three props that are supposed to be the same and they're cast, most probably they perform significantly differently. That's the problem with cast propellers. So a forged machine propeller costs a lot more, but you're getting something for your money. And then it's a economic issue of what do you want to, what's important, cost or performance, or a combination of the both. So there's a definite advantage to a forged machine propeller, but you're also going to pay for it. You're going to pay for the talent, you're going to pay for the machine, you're going to pay for all of that stuff. Ken talked a lot about what goes on behind the scenes to try and build one of these things. It is, as you can see, it's not a trivial exercise. One thing he brushed on was pitch. Most people that build propellers stamp a number on the blade that is the pitch. And there's numerous ways to measure the pitch. If I measure the pitch on a propeller, and Ken measures the pitch on a propeller, and Ron measures the pitch on a propeller, we're all three probably going to come up with different numbers. None of them are right, none of them are wrong. It's just because the pitch is not constant on the propeller, and it depends on the tools you're using and how you do it. So if you're trying to compare propellers, you need to measure at least the pitch in the same way, and probably the same person doing the pitch measuring, because a 26 pitch prop, or a prop that I say is 26 pitch, if you give it to somebody else who is a propeller expert and they measure it, they will probably come up with a different number, just because it's a fairly complicated process to do it, and there is no industry standard in the racing business. In the commercial world, there is a standard, but unfortunately, that standard doesn't capture what you need to know in a racing propeller. So people measure different ways and so forth. I'm going to pass out, I hope there's enough here. I don't think I made enough, but I'll pass, and start passing those out.
Give me one, I'll make copies for you.
Okay. Ken talked a lot about the theory behind and the manufacturing behind. I'm going to hit a little bit on, okay, I'm Joe Doak's boat racer. How do I make my boat go faster? What does this mean to me when I'm trying to make my boat go? And I'm going to give you, there's a little bit of math here. And I'm going to talk a bit about how we do some of the calculations. One of the things we learned with the Budweiser racing team over the years was keeping accurate records really, really makes a big difference. If you don't keep accurate records, you don't know what you were doing. And we also had a reasonably good computer data system on the boat, so we could measure a lot of stuff fairly accurately. Not to disparage boat drivers, but they're really crappy at giving you good data. And that's being really nice. If you want good data on your race boat, you need to have some way of capturing the data, and there's computer systems out now that are reasonably good. They're not terribly expensive, but that's the only way you're really going to get good information. So from a kind of a pitch of, if you want good information, probably ought to think about having some kind of a data system on your Raceboat. As far as measuring some of the things that we would really like to measure, like propeller thrust, so trying to measure how much thrust you have on a propeller shaft pushing the boat. I actually did that on a ski boat for a propeller development program. It was difficult, it was expensive. We did get fairly good data out of it, but from a cost and maintenance standpoint, it's probably impractical on the average race boat. What we had to do is we had to float the motor on linear bearings and actually have the motor floating and grip the motor with a load cell and actually have the whole motor floating. Well, if you think about a race boat, that probably isn't going to work very well. We looked at trying to actually get at the shaft. That was impractical. Nobody builds any instrumentation that will really do that. The handout's kind of out there. Okay. Some basic arithmetic on how you can figure out things on your boat. There's some fairly simple formulas if you're trying to sort out what's going to happen on your race boat. And the first one is, how do you calculate speed? If I give you an engine RPM, a propeller pitch that somebody measured reasonably accurate, if you have a gearbox, a gear ratio, and then this magic number called slip, which we'll talk about a little bit, you can actually compute what the speed of your race boat ought to be at any particular point. And for the unlimiteds, they have a very specific limit on engine RPM, so this becomes fairly important for them. For the piston type boats, most people have somewhat of a limit on their engine before they pitch the rods out the side. And they also would like to have the RPM up somewhere at a reasonable value so they're not lugging the engine. So you can kind of work the formulas forward and backwards, but it's hand calculator and a little bit of arithmetic. And the first formula is your speed is equal to the RPM of the engine times the pitch of the propeller times your gear ratio, which I'll talk about in a moment, times a little sub-arithmetic beforehand, 100 minus the slip of a propeller in percentage. And most propellers are somewhere between 12 and 18% slip, with somewhere in the 14-15% region being fairly typical. You do all of that arithmetic and then you divide it by 105,600 and you'll come up with the speed of the boat in miles an hour. And if somebody wants to know where that 105,600 comes from, talk to me later. I'll show you how that's derived. It is a good number. Gear ratio. There's lots of ways of talking about gear ratio. People talk about an actual ratio. That particular boat, the Slow-Mo 4, had about a 3-to-1 step-up gearbox. In other words, the output shaft turned 3 times the input. Some people talk about a percentage, a 20% over, a 30% over. The gear ratio that you need to use in the formula is the ratio of the output shaft speed to the input shaft speed. So if you have, for instance, a 20% over, that number would be 1.2. In the turbine boats, most of the time there is a reduction gearbox, so the output of the gearbox turns slower than the input. And so on a typical turbine race boat, that number is going to be something in the order of 0.52, 0.54, 0.56. So the output is turning about half input speed. So that's a quick way of measuring or getting some handle on how fast the boat's going to go. Problem is, what's the pitch? Well, it depends on who measures it. And what's the slip? Well, it's a little problem. How do we get the slip? So if you get a new propeller and you don't know this stuff, you kind of run the arithmetic and give it a shot and see how close you come. One thing that we develop or we used extensively when we're running the Budweiser race boat is what I will call performance pitch. What that is it's the pitch of the propeller as it's actually working on the race boat. As Ron showed you, the pitch changes because of shaft angle, it changes because of who measured it. So what really counts is, how's the prop work on the Raceboat? Well, there's a way to figure that out, but you need to have some fairly good information. You need to know at a single point, and the best place to do this is typically at the end of the straightaway when the boat is sort of topped out before it enters the turn. You need to know two things at that point. You need to know the speed of the boat, and you need to know the engine RPM. And you need to know those two at the same point. You can't get one now and one a little bit later. That doesn't work. So if you use this particular formula, if you can capture, and this is where a computer data system actually does a pretty good job because you can get the two at the same time. Take the speed, multiply by 1056, take that number and divide it by the product of the RPM times the gear ratio, and you'll come up with what I call performance pitch. This is how the propeller is really behaving on the Raceboat. And it's going to be some number that's typically significantly less than the measured pitch. But this is how the prop actually behaves. It doesn't matter who measures the propeller. It doesn't matter what the slip is. This is how the propeller behaves on the boat. And when we're running the Budweiser, we kept track of this number on all of the propellers we ran. And this number will vary a little bit depending on water condition and boat ride, but it'll tend to average out. And this is how the propeller really, really behaves. And so if you, for instance, have a boat and the engine is over revving slightly and you need to add a little bit more pitch to the propeller to keep the engine from over revving, if you can compare performance pitches on propellers, this will give you a much better handle on how much you need to change versus a measured pitch. Because measured pitch and slip are two things that aren't really very accurate. If you have a measured pitch, somehow I measured it, Ken measured it, somebody else measured it, and you can calculate the performance pitch, now you can come up with a real slip number. And there's a formula there to calculate slip. Unfortunately, slip isn't very useful. All it's kind of doing is correlating the difference between what somebody measured the propeller and how the propeller actually works on the Raceboat. So if two people measure propellers differently, you're going to have different slip, because slip is a function of how you measure the propeller too. So slip isn't really that useful, other than when you have a new propeller, you haven't actually gathered some performance data on the thing. The best thing you can do is take a shot at it. And we knew at the Budweiser shop the propellers that we were manufacturing, because of the manufacturing process, we had a pretty good idea what the propeller slip was going to be, because we measured them the same, we manufactured them the same, so we had some history, and so we had a reasonably good predictor. But if we got a propeller from somebody else, didn't work very well as far as predicting, because we didn't know how it was measured, so we didn't know what the slip was. And this one thing to note is slip is not the same as propeller efficiency. Propeller efficiency is how well you translate your horsepower in your motor to pushing your boat around the race course. And that's a little difficult to get a handle on until you do some real measuring. But typically, most propellers only put about 60 to 65% of the engine horsepower into pushing the boat. The rest of it is lost in the inefficiency of the propeller, putting water in the air called the rooster tail, and all of those kinds of things. Slip is not a good measure of how well a propeller or how efficient a propeller is. So you can have a propeller that has 12% slip that's a pig, and one that has 17% slip that's a real go-fast prop. So that's another reason that slip is not necessarily a really good indicator. The second page is just some examples. I actually ran some numbers And so you can use the examples and kind of practice with the arithmetic if you want and sort of see what goes on. And there's, the first example is just for an old vintage hydroplane, happens to be the one that I own. 3,800 RPM, 18.5-inch pitch measured by somebody. The gear ratio is about a 2 3/4 to 1 step up, and it all pencils out to the boat ought to do about 154 miles an hour in the ballpark. The next one is an example for a turbine hydroplane. And for any of the turbine guys here, Pyro, this works. 100% RPM for the turbine engines that are using, 26 pitch measured, gear ratio of 0.53, which is sort of in the ballpark, and you run all those numbers with a 14% slip and you come out with about 190 miles an hour. The next example is, given that same basic setup in an unlimited and having some good data, how you can measure an actual performance pitch. And these numbers are actually pretty realistic. These are very close to what we found on the Budweiser. So here's a propeller that has a measured pitch of 26 inches, but its performance pitch is 22.18. And if you work all the numbers, that comes down to a 14.7% slip. Those are pretty realistic numbers for average unlimited hydroplane prop today. A few rules of thumb. Generally, increased rake, which is, Ken described it very well in engineering terms. The easy way to think about it is sort of how far is a blade bent back from being straight up and down. So if you look at this prop, the blade's bent back around 22, 21 degrees, something like that. That's sort of ballpark value for a current unlimited prop. The bigger that number is, in other words, the farther the blade is bent back, in general, the less lift the propeller has. So if you have a boat that the prop is jacking the back end out of the water towards the end of the straightaway, or it's tending to porpoise and hop a little bit, maybe a little bit more rake would keep the back end from getting so high. By the same token, if it's dropping the back end some, maybe a little less rake. So from a practical standpoint, all other things being equal, rake tends to control lift of the propeller. There's some other things that will affect it. As a propeller increases in pitch, it generally also increases in lift a little bit. So as you go up in pitch, typically you have to increase the rake slightly to get the same performance out of the boat. And one thing Ken didn't touch on too much, propellers are boat specific to a great extent. So a prop that works good on, for instance, the Budweiser may not work good on another boat. So trial and error is in order sometimes, and that's why if you have a propeller that works good on your boat and you want to change, you probably need to stay with the same manufacturing process, because if you move to a different manufacturing process or a different design process, you're somewhat starting over from scratch. Now, if you just don't have a clue, then talk to somebody like Ken, who manufactures props, Eric Elstrom, somebody like that. Tell them what you need, and they can kind of make a reasonable guess based on your boat and so forth. When I was involved in designing some propellers for Grand Prix boats, some limited boats, and the best experience or the best success we had doing that was, I would tell people, give me your very best propeller and let me measure it. And we would measure it for a lot of parameters: pitch, rake, cup or effective cup, blade thicknesses, all kinds of things. And then I would ask them, what do you like and what you don't like about the propeller? Take all that information, kind of stir it up, throw it at some software that I wrote, and try and come up with what I thought was a reasonably good propeller. But I would caution the people, the first one probably is going to be okay, but once you run the first one, the second one we can almost guarantee will be good, because once we know how the first one behaves and we have control over the propeller with the software and the machining process, now we can really make a good cut at what the second one's going to be. Generally, we could do pretty good on the first one. And as Ron said, when Ken did one for the Circus, first one out of the bag was really good. That's partly the manufacturing process, partly understanding how it works. But that's kind of the routine on propellers. So, I think for Ken, Ron, and myself, I think we're probably open to questions for a while. Dr. Ken.
Could you speak to choice of propellers with regard to, going down the straightaway, top end is useful, but it's not always the fastest way around the race course, about making choices of propellers with regards to a boat, the performance of the boat, acceleration, things like that.
Okay. The question was, speed at the end of the straightaway isn't everything. It's really time around the course, and how do you balance all of those things? A lot of that is boat specific, because it depends on how the boat handles in the corners too. From a turbine boat standpoint, one of the things that seemed to be fairly important was try and have the engine running at its maximum allowable RPM right before entering the corner. Which is 110% RPM on the gauge. And if you exceed that, you get thrown out. So you can't exceed it, or you're going to get thrown out, or the driver's going to have to back off. If you are significantly under that number, in other words, you're not making the RPM, you're probably suffering on acceleration. So if the boat handles reasonably well in a turn and doesn't do anything bad, if you can get the prop gearbox combination such that you're real close to 110% just about the time you enter the corner, or real close to it, you're probably going to be pretty close to maximum performance. So on a short straightaway course, you're probably going to want to have either a smaller pitch propeller or different gear ratio. On a longer course, you're probably going to want to have a higher pitch propeller, because you can run out farther in the straightaways. A lot of it depends on boat handling in the corners too, and if you have a boat that mishandles in the corners, some of the times you can fix it with a propeller, sometimes you can't, and that's just a pure cut and paste, try it. Other than knowing that rake affects how well the propeller will carry the back end of the boat, but that's somewhat limited as what you can do. If you really have a problem carrying the boat in the corners, tough to fix it with a propeller. Probably need to do something else. Yes, sir?
Who forges the original blade, or who forges?
You mean this nice ugly lump?
In Seattle, what kind of steel is it done? Is it stainless?
The material that's typically used right now is sort of a hybrid stainless. It actually will rust a little bit, and it is very slightly magnetic. It's 138MO is the actual name of it. Nobody in Seattle forges those things. Most of them are done by an outfit down in Berkeley, California by the name of Berkeley Forge. And forgings are, first of all, you have to have a die. In other words, as Ken said, you smack the heck out of the material. You start out with a lump of material and heat it up till it's smoky red hot. It's not melted. It's still it's kind of like the old blacksmith did, where to get it nice and red hot, and there's some specific temperatures, and then they've got a die, 2 dies, and they go ka-whang, ka-whang, ka-whang with some very high-powered presses and swat the thing several times to beat it into that shape. And there's some control on the temperatures and how hard they hit it and so forth. The dies themselves are reasonably expensive. There's 2 or 3 sets of dies kicking around right now. If you call up Berkeley Forge and say, I want some forgings, they're going to ask you, whose dies are you going to use and do you have their permission? So the people that have spent typically about $25,000 for the dies probably are going to want some little remuneration for using the dies. And the other thing on forgings is the first is really expensive because of the setup at the forging house, and after that you're primarily paying for materials. So you usually have to buy about 10 of them at a crack to make it economically feasible. The last batch that I'm aware of, that forging costs somewhere in the $4,000 to $5,000 region just for the forging. So
If you're going to build those, you're going to buy 10 of them at a time?
if you're going to buy 10, you probably get them $4,000 to $5,000 a piece. If you buy one, you're probably going to pay $8,000 to $10,000 for that first one because of the setup at the forging house, because they got to get the dies, they got to put them in a press, they got to do all of this stuff. So it doesn't make sense to buy 1 or 2 forgings. So typically people buy a bunch of them. So somebody's got to write a pretty big check to do that. There's nobody in Seattle that I'm aware of that has the capability of doing that. That's for right now, Berkeley Forge down in Berkeley, California, the folks who are doing most of the forgings.
And how different of a propeller can you make from that? A wide range of variables?
This particular forging, a reasonably wide range of, you start looking at it, and when you're designing a propeller, you have some idea of what you've got for material thickness in the forging, and how much can you maneuver things around. So in an unlimited prop, not a whole lot of maneuvering room in here, but if you're going to build, for instance, an unlimited light prop, which is smaller diameter, smaller blades, you can probably do a bit more maneuvering around inside that forging. There's another forging kicking around for an unlimited that's a fair amount thinner than that. It costs a little bit less money, and it's a little easier to machine because you don't have to remove as much material, but it's very, very limited in what you can do. You're stuck very much in blade shape and those kinds of things. So there's a trade-off of how long do you want to spend in a CNC machine hacking material out for what you want to do also.
Dixon?
Yeah.
I just wanted, there's a good friend of all of ours who couldn't make it tonight, Glenn Davis.
Oh, okay.
And he sent me a couple photos that he wanted me to make copies of and pass around. Well, I spent all night making photocopies in there, so I'm
okay.
here for a minute. So I've done a quick drawing.
Oh, okay.
A boat that he helped tune, and there were 3 different photos, and these are 3 different rooster tails.
Okay.
The effect of the difference with a couple propeller changes. And it was supposed to be a test, kind of just to see if the 3 of you guys could figure out how you go from this rooster tail to this rooster tail with changing nothing but propellers. And
well, the top one's about a 1952 boat. The middle one is about a 1962 boat. And the last one is probably a rather current boat. Now, how's that for skating?
I just don't draw that one.
Would the top one just be lifting it up and then lift disappears, lift and then?
And what would cause that?
Well, it's probably the design of the propeller is
Specifically, we talked about it earlier. What causes lift?
well,
Too much or too little?
the rate.
15 degrees a rake, 17 degrees a rake. Now between here and here.
Keep adding rake.
You don't have that many propellers in the truck. You would want to add rake, but they didn't have rake, but they did have the same 17-degree rake, which is slightly less diameter.
Oh, okay. Diameter, and some of that is just plain experimenting. Some of it you can kind of go at it, but some of it is just plain experimenting too.
Now, some of that, though, could depend on water and wind conditions. Some of those crops might be a little better under certain conditions.
This was all same day, same boat within the same hour. They went out, came back, went out, came back, and went out.
Mm-hmm. This is where testing, I get after people all the time about testing, and Ken talked about testing. Testing is not warming up for the first heat. Now, think about that a little bit. Testing is not warming up for the first heat. Testing is going out and really testing, which means not on a race day, and having a plan and what you're going to actually do. And boat racers as a group are pretty poor at that because they don't get prepared in time and so forth. That's what testing does for you, sorting out that kind of thing.
What's interesting to illustrate that this is an old idea is that one of the reasons Slow-Mo 4 was such a dramatically revolutionary boat was because they tested it way more than they raced it.
Yeah.
And in fact, they even took a film of the instrument panel because they didn't have a computer, and so they can get accurate data.
The other thing that tends to be very useful is taking good videotapes of a boat when it's being tested or even when it's racing, and then spending some time analyzing what's going on. And if the boat, I've seen this numerous times where somewhere after the corner the boat does something really bad. It does a hop and starts flying, and people say, oh my goodness, the boat's way too light, it's flying. Well, if you are taking, I've seen this numerous times, taking videotapes and start backing up and start looking at that thing in the corner, a lot of times what you will find out is it didn't carry the back end very well, and the back end dropped, and with a surface piercing propeller like this that's designed to run halfway out of the water, if it drops down, it generates an incredible amount of lift. Okay, the back end drops, it generates an incredible amount of lift, it blows the back end out. Now the back end's out, the boat does one of these, sponsons hit up here, it does one of these, and that's what you see. It happened way back there. It wasn't that the boat was flying, it's it dropped the back end somewhere back in the corner, probably. But you need the documentation, you need the video to see what's going on that kind of thing. So
the trend we've seen in the Unlimiteds over the last couple of years is they do that. Everybody's fighting for lane one, and you do this 40-mile-an-hour troll up into the top turn, and now you come across the exit buoy coming down to the start line, and Ken kind of talked about earlier about the loads being 2 to 3 times depending on where our game is. How do you take into account that you're going to have to go from doing 40 miles an hour to hit the starting line at obviously not at your top end speed, but you're going to have a compromise somewhere because otherwise you're going to cavitate it as soon as you match on the road, right?
That's a significant problem that has not been dealt with very well. I really don't have a good answer for that. One of the things, a turbine engine has a torque curve that is not like a piston engine. As you drag down the output shaft on a turbine engine, the torque just keeps going up. And at 0 rotation of the output shaft, you will have significant amounts of torque. So when these guys come trolling up to the starting line at 30, 40, 50 miles an hour and plant their foot, the power section of the turbine engine or the gas producer comes up to speed quite rapidly in a matter of a few seconds, maybe 6 or 7 at the most. So by 6 or 7 seconds, you've got maximum power in that engine. Well, the output shaft is still way slow, so what you've got is a huge amount of torque. It's different than a piston engine. And That's what Ken was talking about the loads being a factor of 2, factor of 3 on the propeller. Unlimited propellers don't have a good history of sticking together. Chip?
And maybe an answer to your question is the driver's got to know what he's got on there for a propeller. If they send you out with a propeller that's a big diameter, you know, a lot of pitch propeller, you just as a driver know that it's not an inside start propeller, that you're going to try to carry boat speed on the outside. So it's not, when you drive a boat, you have to, and a lot of that's the communication. Where do you want to start? And they're going to tailor the propeller they give you as to where you want to try to start.
And there's, besides just propeller, there's other issues like you're plowing along and you stand on the gas. Can you see out the front window because now you got all this water coming off the sponson on the windshield? I mean, that's a significant problem. There's been some people that have kind of gotten run into and gotten disqualified and cut off and all kinds of things because they couldn't see out the front window. So trolling up to the starting line at 30 or 40 miles an hour may not be the smartest way to do this thing. I can think of an incident in Seattle here where something like that kind of happened.
Dixon, you mentioned earlier that propellers don't always hang together, and that's a real critical issue for the crew chiefs, and it doesn't bother the drivers so much, but it's for crew that has to put that together. Can maybe all three of you address how do you track the lifespan of a propeller, and when do you sell it to somebody else?
There you go.
When you can't stand it anymore. With the Budweiser, we kept track of number of minutes on the propeller, and every time we ran the propeller, we zyglowed the thing for cracks. That was reasonably successful. Ken, how do you fix this problem?
You know, you would have to study, you would hope that you have a failure mode that is progressive and that is observable. Little two-blade propeller being passed around, you know that it has cracks in it. You know, if it came that way off the machine, I never would have sold it to anybody because I would have been scared it would fail. But once it was done running, I was, you know, certainly happy it made it that far, and you know, maybe it would make it a few more passes. I don't know if it would or wouldn't. But after one had gone through that experience a number of times, you'd have a pretty good predictive model of that. You know, it's sort of a whole art to trying to massage a few extra laps out of these things. It started off costing $10,000 or $15,000, and you know, each lap may be worth a couple $100 or so. But until you have a repeatable process on any of this, how you make it, how it fails, you can't know for sure. All of these are built with some presumed margin of safety, and the only way I know is to do this by experience and to keep careful track of it.
The other, in general, you can probably build a propeller that would last 3 or 4 seasons. It would have very thick blades, be fairly thick in this area. The problem is, it probably isn't going to be a very go-fast propeller. So there's a very definite trade between propeller life and performance. And my observation over the years has been most owners, not necessarily crews, but most owners want a propeller that will last a long time so they don't have to buy a lot of them until it comes to standing on the dock before the final heat. Now they want the one that goes the absolute fastest. So there's a trade-off there, and I know some teams in the past have actually had propellers that they use for kind of qualifying easy heats that were not real zinger propellers, but they had a lot of life in them because they were kind of thicker and so forth. And then they had the, what I call a hand grenade with a pin pulled. Go fast, but was not going to last very long, and that's a conscious decision you make. We knew at the Budweiser, based on engine power we were allowed, and a little bit on boat ride, kind of how long a propeller would last, and they have a limited life.
We've we've never had, nor do I expect to have, a customer come into our shop and say, hey, I really need to hire you to design a propeller to finish second or third. Never happened. I don't expect it will. Everybody buys one of these things wants to win with it, and it's necessarily a compromise. The additional performance is going to come at the price of reliability, predictability, and longevity. And there's just no way around that. It's like that in any form of performance endeavor.
Yes, and on an unlimited, when one of these comes unraveled, there's a $15,000 propeller typically, or give or take a little depending on what you pay for it, but that's a small part of the total repair bill because you typically rip the rear strut out of the boat, you yank the drive line out, you screw up the bottom. If you're lucky, you don't tag the gearbox and the motor. So a lost blade on a propeller is probably, on an unlimited, is probably a $75,000 to $100,000 hit. Well,
an interesting question would be, how much, assuming it were possible, what sort of premium would someone pay to have a propeller whose demise was readily observable? This would mean, of course, that you could stop using it a lap or two before it failed. My guess is that people would be willing to pay a pretty good premium. I haven't figured out how to make one that way, but it's an interesting proposition.
Yeah, Ken.
There was a period when they have catastrophic failures and they break at the hub. I mean, guys are like glowing. There's no way to. Guys are checking and they'll still break. Of course, is that a materials failure? I mean, what? Do you have any theories about why? I mean, they all flex. Some fail, some don't.
Most of the blades that I've seen come off start as a fatigue failure. That's not 100%, but most of them do, where you can see that prior to the blade actually separating, there was some amount of cracking going on, and there's a process for observing that. You can see what a fatigue failure looks like. Zyglowing is definitely a lot of technique involved. It is not something that you just pick up and do the first time. When we were running the Budweiser, Mike Campbell did most of our propeller zyglowing work. He was incredibly good at it, and he was picking up cracks that were very, very small, and ones that I think a lot of people would not see, because he was very careful, he was very meticulous. And once a crack starts, they propagate rather rapidly on the propellers. There have been, I'm aware of a few occasions where blades have come off with no indication of prior fatigue failure. Now, did somebody hit something in the Detroit River, the Madison River, with all the junk floating around? I don't know.
It might be, just guessing, it might be that one could, for example, look at an acoustic signature of the propeller under use and monitor that. And it might be that you could determine a change in that as a result of the vibration frequency changing due to diminished section as this starts to break apart. And maybe one could come up with a method that way that would, light up a little bell on the dashboard or something.
Yeah. One more quick question.
Yeah, let me add one. There have been a few propellers where it's been identified as a material failure. There's been a flaw in the metal. Not very much in forged propellers. There have been a couple where the forging has had a flaw in it. Most of the material flaws have been in cast propellers.
Well, I've been very puzzled as to why offshore boats have chosen to use what they have. That doesn't mean it's a bad choice. It wasn't obvious to me. The offshore boat is designed much differently than a hydroplane, and it is not dependent, as a hydroplane is, for support at the transom of the boat by propeller lift. So there's a lot of differences in the hull I think there are a lot of reasons why they choose to use what they do. I'm not sure they're necessarily bad choices, but the only compelling one that I have heard is that the boats tend to vibrate a lot less with the 5-blade as opposed to, or sorry, with the 5-blade than with the 3-blade. And I've heard that from very reliable sources. That could be for a whole variety of reasons. It could be they got crummy propellers. It could be there's, you know, resonance in the system. I wouldn't want to speculate without knowing a little bit more. But I can virtually assure you that there's nothing magic about a particular number of blades.
Okay. There was one occasion where a 5-bladed propeller was manufactured for an unlimited as an experiment, and it actually was tried. It did not work well because it had a significant amount of lift in it, and the boat, it actually picked the back end of the boat up to the point where the boat was riding forward on the sponsons and kind of steered around like this. Now, that could probably be fixed, but what it was essentially same basic design we're using for a 3-bladed with just 5 blades. So I mean, it was a nice looking propeller, it was well manufactured, but adding those 2 extra blades changed the characteristic of the propeller enough that it was essentially virtually undrivable on the boat. It was definitely not raceable. And so that particular project was scrapped. Personal experience running my old restored unlimited, the boat running a 2-bladed propeller, there is definite vibration in the boat, and if you think about it, with a 2-bladed propeller you have at some point basically no blades in the water, so you have this very definite cyclic load on the drive line as each blade's going in. Put a 3-bladed propeller on the boat, there is significantly less boat vibration from a driver's standpoint because you always have one blade in the water. And that's probably easier on the drive line, the gearbox, and all of those kinds of things.
At a certain RPM, is there a certain RPM where these propellers are more efficient, or they basically start losing efficiency?
Propeller theory says that there is a pitch diameter ratio that you should not exceed. And this kind of comes back from basic propeller theory. Well, I'm not so sure about the limiteds, but the unlimited class of boats has a rule that says you can only be 16 inches in diameter. So if you stick with some kind of the pitch can't be more than 1.7 times the diameter or something like that, that kind of limits your pitch. Older race boats like these guys here, like the slow-mos and that vintage, typically turn the propellers 12 to 14,000 RPM. They typically ran 3-to-1 step-up gearboxes and about 4,000 on the engine, maybe a little bit more. Up through the kind of late 60s, early 70s, people started slowing the propellers down and increasing the pitch, and the boat handling improved and the boat performance improved, but also the boat designs changed. So you get to something like the Atlas here. That's a significantly different hull design, but also the gearbox ratio is different, so they were turning the propeller slower, more pitch. Current Unlimiteds now seems to work pretty good around 9,000 RPM with about a 26 pitch, whatever that means, propeller. On the Bud, we tried some lower ratios, bigger pitches, and we did find out that there's a certain point when you're stuck with a certain diameter that as you increase the pitch, the boat handling kind of goes to pot. The propellers start walking the back end around, they don't behave as well, so we just empirically sort of decided that there was a certain pitch that we go above that and the performance starts to decrease. Now, if we were allowed to go up in diameter and pitch, we might been able to get around that, but we were limited to 16 inches in diameter by the rules. So that's it. Chip.
the other thing that goes into what you were just talking about is the race course itself. For example, Madison has such a narrow corner that if you have so much diameter, it literally you can't drive the boat because the propeller with diameter that would work at Evansville literally walks the back end of the boat all the way around. So the size and the shape of the race course also plays a part into deciding on pitch and diameter. So it's boat specific and race course specific.
Yeah. So
I would also add that it may be water specific, water condition specific.
Yeah.
One thing to bear in mind is that as these are partially submerged propellers, as the ride height changes, if you have a relatively small diameter propeller and you change your ride height by 1 inch and you're only submerged 2 inches, you've reduced your submergence by half of what you had. My normal preference would be to put as large a propeller on as you possibly could get away with because the effect of varied submergence is diminished then. But there may be other good or ill effects that go with that. Additionally, as you vary the submergence on the propeller, if we complicate this a little bit by saying that we've got pitch progression in the propeller, meaning that the pitch here is less than the pitch further back and further back, then as we change the submergence, the propeller is acting in a different pitch range at different levels of submergence. When we submerge this fully, meaning half in this case, we're seeing the entire blade, and the varied pitch across the entire blade is acting. That may be good or bad. As we submerge the blade only this much, as we might, for example, at the end of the straightaway, we're only seeing the pitch that appears on the propeller in this zone of the propeller, which is a very limited angular range. And on most propellers, that typically would be the higher end of the pitch range. So effectively, what you have is sort of a quasi-automatic transmission here, which is shifting gears for you as you change the submergence. Again, that may be good or bad. I'm just saying it complicates the problem.
And one other thing is, nobody really knows for sure that I'm aware of exactly where the propeller rides. A lot of people that think they know, but when it comes down to it, when you start asking the hard question, how do you really know? Well, the answers get real fuzzy really fast. We tried, at one point on the Budweiser, we actually tried to measure ride heights. That is not an easy thing to do. And we got a little bit of data on a couple of runs that was not real definitive, and the probe we were using, the way we were doing it, I think Chip was driving and I think it bent and I think it got the boat real squirrely and real quick. So it wasn't exactly a successful experiment, but that was a specific testing. We spent some money, we tried to do that, and it wasn't successful. So we didn't really gather any good data out of the thing. So I've tried to watch boats running at places like Phoenix, where you can get down close to the water and look, and it's real difficult to tell. Somewhere kind of around the bottom of the strut, or maybe up and down a little bit, but I don't think anybody really knows that I'm aware of.
Any specific numbers or ideas on saltwater and freshwater?
We have some fairly good data. The slip tends to go down 1% or so in saltwater. Saltwater is more dense than freshwater. And so one of the things that complicates the issue there is your water speed indicator isn't as accurate because it's calibrated for freshwater versus saltwater. So boats appear to go faster because the water speed indicator reads a bigger number because the water is denser, but the data we gathered, we saw an effective increase in what I would call performance pitch that was measurable in saltwater. So we would make an adjustment on saltwater. We would use a effectively slightly smaller pitch propeller because the water's thicker, so the propeller pushes a little bit better.
One would conclude that you probably see a little bit more lift with the same propeller configuration. So,
yeah, and we didn't really have a way of measuring lift nor how far the boat was out. So, but yeah, saltwater Salt water makes a propeller act like it's got slightly more pitch. Exactly how much is very propeller dependent, but there's an effect there that you see. I'm about talked out.
Could you
One
tell?
last perspective on history. I'd like to hear from you and Ron from '66.
Say, my hearing aids aren't working real good. Speak up.
We talked a lot about tonight what's current and what's recent, and I'd like to hear from you and Ron about what you looked at in these types of points of view in 1966 with those three blades. It ought to be quite a comparison, I have to think.
You're on.
Sorry, Ron.
Maybe you can tell me it's precise. I heard a little bit of what he said, but my hearing's worse than yours.
That's hard to believe. Well, kind of, I think the question was, back in about 1966, what were we looking at? Is that?
That's right. What kind of conceptual things were you looking at, and how to set up the three-blade for that first front engine boat, and
Yeah.
that type of thing?
Well, Dixon may know more about this than I. That was a particular hard spot in my life. In 1966, Bardol was the first rear-engine white transom low profile boat on the water in the unlimited class. And I had great hopes for it. And in fact, it was very fast. One of the reasons that it failed was I insisted on a three-blade propeller, and they were able to find one somewhere. I've forgotten where they got it. They ran it and thought that maybe the performance would get improved if they thinned it down. So it was taken out to Howard Kruger, he's gone now, but he was a great friend of mine and worked on propellers all his life, mostly tugboat propellers, but we hydro guys talked him into scaling things down and working on the little props. And he did, and he thinned it down and it went faster. And they were very encouraged, and so they took it back again to thin it down some more. So he did, and it went faster. So they took it back a third time, and he said, no, it's already too thin. I'm not going to touch it anymore. Now, the boat crashed, as we all know, and Ronnie Musson lost his life. And for, I don't know how many years, 18 or 20 years, I didn't know why. And I lived with that. When I went to Ronnie Musson's funeral, I was 40 pounds lighter than when the day he crashed. So to me, it was probably the toughest spot in my life, one of them anyway. I never found out till 18 or 20 years later about this thinning down routine. And what had happened was the boat always, from day one, had a vibration, and nobody could find it. They tried everything to pin down this vibration. And they finally just said, well, it's there, and the boat seems to be running, and it's going, so I guess whatever it is, it must be okay. And the way we now see it, many, many years later, he won the first heat on Saturday, which was a new world competition record. And on Sunday, he was leading the heat. And suddenly, if you study the videos of it, movies, the rooster tail began to look like the first one on the top there. What is surmised is that the first thing that happened was a chunk of the trailing edge of perhaps a small piece of the trailing edge of the propeller broke off. But the boat was still going. And Ronnie probably said to himself, boy, that vibration is getting worse, but I'm still out in front. But then the boat started riding poorly, and the rooster tail it was so jagged, it was obvious something was wrong. And before that lap finished, as he was crossing the start-finish line, Notre Dame passed him outside of him, so you can't see what happened. Generally, there are no real good films of what happened from inside the race course to see what happened. But apparently what happened is then the whole blade came off, the propeller disintegrated, and ripped a strut loose from the bottom of the boat. And normally, in today's world, when that happens, it pulls the shaft out of the gearbox. That particular gearbox was as big as this podium here and built like no tomorrow. And
Yes.
the shaft wouldn't come out of the gearbox. The engine was still running momentarily with the strut and the shaft bent, whapping around, tore the back end of the boat off, stuffed the nose down. The river was 4 feet deep. The bow of the boat went into the bottom of the river, and everything that was above the waterline broke off and went down the river. So thinning the propeller made it go fast. But obviously, we didn't know then, no one knew then, how thin can you go? It was too thin. And that's why Ken and Dixon, when they designed a propeller, they would love to make it thin. You know, I mean, the obvious advantage of making a thinner propeller, at least in certain areas. It would be nice to do that, but you're motivated by what could happen. So you don't do it.
The other thing, back in that era, when you got a propeller, you went to somebody like Carey or one Stannis or one of the propeller builders, and you said, I want a 3-bladed propeller, and you kind of got what you got. You didn't have a whole lot of choice. You could sort of tell them what kind of pitch you got, but rake and blade shape and all of that was sort of what you got. So now we have a much better handle on building propellers, understanding what goes on, and since they're built locally, we can control a lot. Back then, you kind of got what you got, what was available at the propeller store, and it was a real crapshoot as to what you got. And 3-bladed propellers were very rare. There weren't very many of them around, and you kind of had what you had. And that was part of the problem also, is that propeller, unfortunately, probably wasn't very well matched to the boat, but it was the only thing that was available.
And it was undoubtedly a casting.
Yeah.
That propeller and the strut and the shaft are in the back corner of the museum.
Mm-hmm.
And before we put it in the case, we looked very closely at the fracture, and you can see the crack propagate from the back of the point where the blade attaches to the hub, and you can see the little, almost like tree rings, where the crack propagates forward until it gets about 3/4 of an inch, and then there's a catastrophic failure where the blade breaks clean off.
You people are marvelous. I can't believe it.
You people are
You
marvelous.
haven't found it. You haven't fallen.
I think we've probably gone long enough. If people want sort of individual questions, I think I'll hang around for a little bit. I think Ron and Ken have agreed we'll hang around a little bit and so forth, but we won't keep the rest of you folks captured. So thank you for your attention. Hope we didn't baffle you with BS. We actually gave you a little bit of information.
Thank you everyone for coming. Remember,